this is actually a very good point because I was reasonably happy with the 2 videos that we had in training, in neural net training. But the 3rd video is something that I was not quite happy about 2 years ago. So I'm going to give it another try. Okay, and I'm going to make some changes. And in fact, if you're interested, you can watch the video from 2 years ago. It's actually also on the class wiki, and it's just the March 14th, I believe, is the date. And then you can compare that against what I do today. So you never know, because when you try new things, it may not work. Okay, so if it doesn't work well, you have the other video to fall back to. Okay, so before we move on, is there any question from the previous 2 videos so far? Was it reasonably clear? Okay, in that case, we would start from this point. So we talk about training, and the training is based on the loss function, right? And so you have a neural net where you have any kind of function, machine learning function. If you go to the end, you have an answer, right? You can compare the answer with what the answer should be during your training process. So that's the benefit of having a label. If you don't have label, there are all kinds of more sophisticated ways to try to get around that, right? That there are different kinds of learning. But let's say, in most cases, it's still much better if you have the labels, and so that you can compare the label with the inference result, and then the difference generates an error value, right? That error value becomes the criteria for training, because if the error value becomes too high, that means that the network is not doing the right things. And so when I was young, we went to this elementary school, and the teacher, every time after the test, right? At the test is the inference. So we have all the neural nets. Then we take the math test, and after the test, the teacher will hand back the papers. So you get 99 points, you get 87 points, you get the 92 points, and then the teacher will whip out a stick. And then everyone was lined up. Okay, so you missed one question, and so one lash. And then you missed 2 questions, right? So that's the training. Okay, so the error function, that directs the number of lashes, and then the pain would change the neural net, and then so next time we can get the question right. So that was the human neural net training process, but it's not that different from what we're talking about here. So basically, we have let's say the network, and the simple network could be a linear function, w times x plus b. W is the weight function, x is the input, and then b is the bias, right? So we have that simple function, and then we define the final output to be an activation, the layer, which is a s of the output of the final linear output g. So we do a kind of a judgment based on a s function, and then we say that we define the error to be y minus y cap. So in the human training case, we have 100% divided by the whatever points, and then whatever points is the linear function of which question you got right or wrong, right? So this is all. There's nothing different between the various disciplines. So the education system know about neural net training for hundreds of years, right? But after a while, people, I don't think it's even legal to have to do the lashes anymore. So some people claim that that's the reason why the math education is so bad. So you need to go back to the human training. So no matter what, I'm not going to institute the human neural net training in this class. Okay, so be set assured that we're not going to do anything like that here. So y cap is the true label, and s is the sigmoid function. So then you can do the w. Essentially, you can say if the error value is too high, meaning that I can run a batch of inputs through the neural net and check if each one is, we're getting the right answer or not, right? So then you can just accumulate all the error values and say, okay, if I have 100 inputs, and then my error value goes beyond, so average error across the 100 input goes beyond a certain value, then I need to whip out my stick, right? So that's that's the criteria. And then I need to begin to say, okay, what's wrong with this? What's wrong is because I have some kind of W, right? the coefficients. So the W's are the values that apply to the input and eventually get the answer. So the W values must be not right. So I'm going to ask, how sensitive is each W value, right? Each W value to the final error. So if I increase the W value a little bit, let's say the W value by 0.1, do I have an increased error or decreased error? If I increase the W value and then the error actually increases, right? Increases, then I should try to decrease, right, the W value, right? So, but if I increase the W value and then the error value decreases, then I should increase the W value. So that's exactly what this delta E delta W is about. If I can figure out for the W, which direction I should adjust the W value so that the error value will either go up or down, right? Then I can go ahead and change the W. Then I know which direction I should change the W and how much to change W. So, that's the reason why we're going to have a delta E delta W. Delta E delta W tells us how sensitive is E over W, right? If I make a little bit change in W, what is the amount of change I'm going to see in E? That's exactly what delta E delta W means. It's the rate of change of E as a function of W, right? So that's the mathematical definition. So with calculus, we know that we have a chain rule. The chain rule is that whenever we have a composite function of W, E is a composite function of W, then when we do the differentiation, we can start with the direct function of W. In this case, is G, and then G, the S is a function of G is a function of W, S is a function of G, and Y is a function of S, and E is a function of Y. So it's eventually we will go through the chain and get to an E. So E is really a composite function, okay, composite function of W through a few definitions, right? So we can do the chain rule, which is the product rule, and then we can say, whenever we do this differentiation, we're really doing individual differentiations of each level of the function definition, and then multiply them together. And each one is actually quite well defined, because G over W, when I look at G as a function of W, if I do a differentiation of X, of G over X, then X is X to the first, right? So what I'll do is I'll get rid of the constant. Constant doesn't change. So when you do a differentiation, constant goes away, and then whenever I have your X, the differentiation is just W. So then I have if I differentiate over W, the answer is X. So that's X right here. And then the sigmoid is just the sigmoid prime, and then one here because we have a Y, abstract value, absolute value, and then you do the positive side, you do the negative side. Either side is a linear function, so you end up with 1, right? The coefficient is 1 for the Y, and then you have the delta E delta Y. And so this is the one here, and then so the Y over S is just the Y is just the sigmoid value, so it's just the S itself, so that's for Y. So you multiply the whole thing together, you get the answer. So so that's what it is, and then you take the sigmoid function, and then you say, okay, I do a little bit of differentiation, and I get the value, the answer. So that's where we are. And so now the question is, that sounds great, but what I'm trying to do is I'm trying to adjust the weights, okay, of the neural net. And these weights are actually, a little bit of a, thorny, because these weights are not just single values. These weights are matrices, right? These are convolution mask or convolution filter matrices. So we're going to have a huge number of these matrices, and each matrix is a k by k matrix. So we're not talking about a single value. We're talking about many, many elements, right, from quite a few matrices. So we're going to try to figure out how important is each of these elements for the error. If I change one of these error, element values, does the error go up or down? Does that make sense? So we need to essentially figure out how we're going to adjust all the elements when we do the backpropagation, right? So we're going to figure out how to calculate the delta E, delta W, but that's really about delta E over each of these delta W element of the element, okay? So it is a matrix that gives the influence of each W element on the error, and it's the same dimension as the W matrix, because we're trying to tell how important is each element, right? Each element to the output value. That means that we should have as many of these delta E, delta W's as the number of elements in the weight matrices, right? One for each position, right? Okay. So the calculation is about generating each element of the delta E, delta W matrix, and for any given P and Q values, delta E, delta W, PQ. So this is a given, any given one filter, right? This is within a filter. Then is the sum of delta E, delta Y times delta Y, delta W. So because E is going to be a function of your output, right? So it's a function of your output. And the output is also a function of W, right? So when I try to figure out delta E, delta W, I can, if I know delta E, delta Y, and then I can derive delta Y, delta W, I multiply them together, I get the answer. But this needs to be done for every element, right? Every element, so that all the answers are going to be marked with these, indices, because that's, we're calculating based on every element. Okay? Any questions? If not, let's start. Let's take a look at the formula. Convolution network, each output value, okay, each output value is the sum of, the sum of input elements times the corresponding W element, right? The convolution, that's the convolution. So it's summed over the dimensions of the dimensions of the filter. So for 3 by 3, it will be 3 here, right? It will be a total of 9 element, 9 of these products summed together, right? So so that's the kind of the forward definition. So when we look at delta E, delta W, we're going to essentially do delta E, delta W, and delta E, which is delta E, delta Y, and delta Y W, delta W. We're going to assume the following. One is we know this, okay, and in general, if you have a neural net, you're going to have a final output. And the final output is going to be somehow related to the error. And it's usually a distance between the output, the final output, and the supposed output, right? The correct output. There's some kind of distance measure. So in general, it's fairly straightforward to measure that distance. And so you have an output value, And then as a function, so then you can define the distance as the discrepancy between the label and the output with L1 distance or Euclidean distance or cosine distance whatsoever, right? You can define any of those distances. Once you define the distances, you have the function, and then you can do the differentiation, and you're done. So that's usually okay. But at least for the last stage of the network, we will have this. So now we're going to ask, if the last stage is a convolution layer, okay, if the last stage is a convolution layer, how do we calculate the delta y, delta w for all the filters, all the filter weights in that convolution layer? Make sense? Right? So the answer is this. And then that's the mathematician. Okay, the mathematician will say, simple. I stare at this a little bit, and then I give you this. And this is the answer. You say, how come? You say, that's just the way it is. Look at how beautiful it is. Right? And then the engineers look at it and say, are you sure? Right? So I'm an engineer, so I'm going to do a different way. So for engineer, we need to make sure that we know how these things are really computed and where these things come from. So we're not mathematicians. So this is just a quick review of the convolution layer. We'll take the inputs, right? We'll take these inputs, the input channels or input feature maps, right? Each is the input feature map here, and then we have these the filters, and then we have the output. So a filter, there's one filter for each input and output pair, right? So the filters, if we have 3 inputs and just 1 output, then we're going to have 3 filters. If we have 3 inputs and 2 outputs, then we have 6 filters, right? So each filter is that belongs to a pair of input and output. It transforms the input into contributions of the output. And all the inputs of the convolution layer will affect every output. So we have convolution, contribution, convolution, contribution, and convolution, contribution. Right? So this is just a review, right? It should be pretty straightforward. So now let's take a look. Remember, we're trying to figure out how important is each W value, right? Is each W value to the delta E to the contribution of the Y, right? Because we already decomposed the problem into delta E, delta Y, and then delta Y, delta W. So we already know the delta E, delta Y for each layer. Now we're trying to figure out how important is each W for every output value. Now it also should be pretty clear that Y is a feature map. So Y is also matrix, right? There are many, many Y elements. So we're going to be looking at how important is each W element to each Y element, okay? So that we can do the computation, right? So remember that, right? How important is each W element to the value of each Y element? So we have a huge number of these correspondences, right? So we need to figure out how to systematically establish and calculate those differences. Mathematicians don't care. They just say that here's the formula, okay, and I'm going to go out for dinner now. The engineers need to know how to calculate all these values so that we can actually produce a working system. That's why we're paid more, okay? So they drink more, we're paid more. So let's take one of the elements. So W0000. This is the feature map between input channel 0 and output channel 0. The first one is output channel, the second one is input channel, and then you have the index within that filter, right? the last two dimensions. Let's say if when I look at the contribution of x00, okay, of w00, this element to the output elements, I'm going to be multiplying the w, right, to some x elements, right? When I generate the y, the way that I'm doing this, I'm doing the convolution of x input through these filters, right? So the y is really x convolved with w in some way, right? In some way, and then generate all the y values, right? That's the convolution. This is the reason why I did that review, right? So the importance of every w should intuitively be magnified by the x values. Every contribution to y is some kind of product of an x element, a w element, and accumulate, right? So the importance of each w should be somehow tied to an x value, because the x value is multiplied with that w value, right? W element value. So if the x value is big, then any small change of the w value will make a big difference in the y value, right? So intuitively, the importance of these w values should be defined by the x values. So now let's take a look at how it works. So w0000 is going to contribute to y000, okay, y00 through the multiplication with x00, okay? So basically, we're going to be, remember, w is in between a particular input feature map and a particular output feature map, right? So when I want to know the importance of w0000 to y000, it's the zeros output feature map, right? So I also know that the way that w00 is going to contribute to the y0 feature map is by multiplying with the x feature map. I also know that during convolution, w00, the last two zeros tells me that it's the upper corner element of the filter. And that's going to be multiplied with x00, okay, with x00, and contribute to the y00. Okay, that's the convolution part, right? I'm going to take that little chunk, the little, the square in x, convolve that with the filter, and the 0 parts are going to multiply together, accumulate to y00, right? So this is just the definition of the convolution operation. I also know that I'm going to contribute, to y01 with x01. That is, the w is, you can shift the w a little bit in the convolution process to the right by 1, and that w0 is going to be multiplied with x01, and that it belongs to the next convolution, and that's going to be contributing to y01, right? So I know all these facts, and in general, this w is going to make contribution to all these y elements, right? Which makes sense, because the filter is shared across all the elements. So the filter is going to be kind of shifted around in the input and contribute to the output, right? So that filter, that same w00 element, okay, is going to be contributing to all these y elements, right? By multiplying with all these x elements, right? So you should be expecting a total number of terms. We should be, for any size of the output dimension, right? Output dimension, we should have, the H out times W out terms in this form. Okay, we should be able to, let's say if the output image is 1,000 pixels by 1,000 pixels, we should see 1,000,000 of these things. Okay, and it's really telling us how that W0 value is influencing the Y values through multiplication with all the X values in those convolution processes. Does that make sense? Okay, so this convolution process can be used to calculate delta E, delta W this way. Delta, when I look at the input, remember the input is delta E, delta Y. Right? This is the input. It's coming in as matrices. They're exactly the same dimension as the output feature map because we're trying to look at what this gives is the importance of every output feature map element's importance to the error. Right? That's what we know so far. We know how important is every output feature map value to the error value. So that's why these matrices are coming in the form of output feature map matrices. Right? You give the importance of every element. Given the element, so let's say I know how important this Y0 and then 0, 0 is, the output feature map 0, and then the element 0, 0 in that feature map is for the error. When this is a known value, I'm going to just go into the matrix and I see that value. And in order for me to know the importance of W to E, I'm going to need to go through this intermediate function. The intermediate function is how the W affects all these Y's, right? So basically, I'm trying to figure out how many ways are there for the W, for that W000 to get to the error value. What are all the paths? And each path, how is that W value magnified, right? And if I add all of them together, then I get the total influence of W on the error. Does that make sense? Right? So this is really tracking all the ways a particular W element is going to influence the error value. Okay? So here, I see W00 can affect the error through Y00. Okay? So this is one path. And then I can see another path, W00 can go through Y001, Y001 here, right? And also influence the error. So I'm going, if I have 1,000 by 1,000, output image, output feature map, I'm going to have 1,000,000 of these paths, okay, for W00 to influence the error, right? So I need to count, and each one will come down to, what is this? Remember, W00 is influencing Y000 by multiplying with X00. There's a reason why I gave you that term. So when I do the partial differentiation of Y000 against W0000, I'm going to get X000, right? That's a simple linear differentiation. So that's why this term will end up being the simple X000. So what I'm going to see is that in order for me to calculate the importance of each W element for the error, I'm going to need to actually multiply the input element. This is the input into the back propagation to this layer, right? Then I'll need to take the element from that matrix, this element from the matrix, and multiply by the input value to the layer, the X000. Okay? And this gives us a very clear pattern that we're doing essentially a convolution, if you think about it. We're using this thing as, let's say, a convolution filter. We can treat this as a convolution filter. And then this thing as the input image, okay? And we're going to move this convolution the filter a few times. And each time, each convolution gives me the delta E over delta W for a particular weight element. And if you think about it, it makes perfect sense because the input image is bigger than the output image for our convolution layer. Remember that? The input image is slightly bigger than the output image because, let's say if you have a 3x3 convolution filter, you're going to actually lose the side, each edge, right? So the output is going to be the input dimension minus 2 on each side, right, for a 3x3. So the input is slightly smaller. So the picture you should be thinking about is this. When we have the original convolution, we have a small filter, and we move the filter around, right? We move the filter around and generate a slightly smaller image, output image. It's slightly smaller in each side, on each side, because we lost the we lost the kind of the aprons, the halos for when we generated the output, right? Now, what we're doing here is that we're taking the same input x, and now we're using a matrix that is of the same size, as the output, and so we're actually using something very similar size as the filter. And each corresponding position of these elements are multiplied together, right? Just like the convolution. So how many times can we move this thing? Not too many times, because each time we apply it is almost the whole image, right? So we can almost only move it the same number of times as the filter, right? As the filter, the original filter. So that makes sense because each time we move it, we generate the delta E, delta W for that filter value. Does that make sense? Okay. If it makes sense, great. If it doesn't make sense, go home and watch the video again. Okay? And if it makes sense, try to explain that to your roommate. And this is one of those things that really you should try to explain once. And once you know how to explain it, you'll never forget it. Okay? So this is a very big, conceptually, this can be a very, very big convolution. And we're treating the output, the delta E, delta Y as a big convolution filter, right? And generate the delta E, delta W for relatively small original convolution filter weight parameters. Okay? And this will actually affect how we're going to calculate it using GPUs and so on. Okay? Most people know, most people will immediately tell you, yeah, training is just matrix multiplication, right? But very few people actually understand where the matrices come from, and what are the characteristics of the matrices, how do we implement it efficiently, and that's where the engineers start to come in. Okay, so any questions so far? Do I need to repeat any of these? Right? It's very important for you to see that we're trying to adjust the weights, right? Don't lose sight of that. We're trying to adjust the weights. In order to adjust the weights, we are asking how important, for every element, we're going to ask, how important is this element to the error? If I increase the element of this, the value of this element, then is the error going to increase or decrease? Right? And so I'm asking the same question for all the elements, and then I'll figure out which direction we should change the value of the W, right? So for each element, so that I can reduce the error, right? So then what we need to find out is how, for each layer, we're going to have delta E, delta Y. We're going to have the importance of each output value for the error. That's a given for each layer, because we're going to start from the very end, we're going to go backwards. So every time we reach an error, we already know delta E, delta Y. And these are coming as matrices of the same dimensions as the output feature maps, because each one gives you the importance of the output feature map element, right? So you have that, and then you're going to find out all the sneaky paths that the every W element, all the possible paths for that W element to affect any particular Y element. And that's what we listed here. And this gives us once you analyze it, you say, this is a convolution operation between the output, the input feature map, and the delta E, delta Y, the matrix, okay? And now you can do a convolution calculation. You move it around a little bit, and you get all the delta E, delta W's. Make sense? Okay. So that should be simple. And if you understand this explanation better, you go back home and watch the video from 2 years ago. I explained it a little bit differently 2 years ago, but I think this is more intuitive. Okay, so if you like the other explanation better when you watch that other video, let me know. Okay. So so the convolution layer, since each W element affects all the elements of Y here, we should accumulate gradient over all the pixels in the corresponding output feature. That is, all the output features will somehow be affected by every element. So we need to kind of give the importance. We need to contribute that importance back into each W element, right? Through all these paths. And that's what we're going to do in the code. So what are we doing? We initialize this to 0, and then we're going to we're going to the H and W. So this is an output feature map, H and W. So we iterate through all the elements of the H and W here, and we're going to pick a particular input and particular output, because that's the pair, right? And then we're going to go through the P's and Q's. So each iteration will allow us to write into a different P and Q element of the weight. The way I would organize the code, this is the code that Ginsberg gave me for the textbook. The way I would have organized the code, if I try to make it more readable, is that I'm going to make these two the outermost loop, because these outermost loop will be generating one output. Actually, not output. The outermost loop will be the C and the N. So these are the two outermost loops, because that defines the particular filter that I'll be working on. Right? Remember, each combination of that input filter and output filter defines the filter that I should be looking at. So I use those as the two output levels, and then I will use the P and Q as the second level, the next level, because I will be generating one element, right? The importance of one original filter element in each of these iterations, right? And finally, I will go into the H and W as the innermost loop, because that goes through all the output feature map elements, all the output feature map elements, and identify the input that correspond to each of these output feature elements, and then do the accumulation for the weight. So that will make the code more readable and more kind of logical. It may not be the best performing code, by the way, because the locality and so on may be different, right? But in terms of understandability, that will be probably the best way to express it. Any questions? So that's the sequential code. And then you can map the different dimensions of the different loop levels into the kernels, right? So you could write a CUDA kernel based on this piece of code, and you will have a training, convolution neural net training code. Any questions? No? Okay. So now let's look at a simple example here. This is the output feature map, what we call the output feature map gradient value, right? So delta E, delta Y for all the Y elements, right? And these are the original inputs to the layer, right? So original inputs. We just said that we're going to be doing a convolution, right? Convolution of this thing here, and here, and here. And we're going to generate the first three elements in the delta E, delta W. Right? So that should give you further kind of a visual intuition. Okay? Now, so I said, okay, this is, why is a convolution? So when I take, let's say x1, and then I'm going to contribute to, let's say W output 1, then I'm going to go through this convolution process, do the addition, and generate the delta E, delta W, right? So it's a little bit deceiving here because I'm using a 3x3 field, original field, the W, right? The W is 3x3, and it seems like this delta E, delta Y is very small in this example. But you really should be thinking about something like hundreds of elements in each dimension, and this is just slightly smaller, right? This thing is going to be just slightly smaller than this thing, right? The difference is defined by the dimension here, right? So we're talking about, in practice, fairly large input feature maps, fairly large output feature map dimension gradients, and then we're going to do the convolution and generate fairly small dimensions, but many of the, quite a few of them, the matrix elements. Okay. So I don't think we need to go through all those illustrations anymore. I think we should have made the point pretty clear. So we're going to, essentially doing convolution, and then accumulate into a delta E and so on. So, and then the same input will also be used again for generating this output, right? Generate this W, and then the same input will be used to generate this W. So each input will be used multiple times, okay, in that calculation process, right? And each output will also be used multiple times. And this sounds familiar, should sound familiar to you, right? In the original neural forward path, we have each input, right, will be used multiple times to generate the output feature maps, right? And the weights are also used, each weight is going to be used, multiple times in terms of the, inside each input feature map, right? So this should sound, somewhat familiar to you. So we can formulate this way. We can treat the delta E, delta Y the same way that we treated the filters in the forward propagation. We can just lay them out. We can lay them out, linearize it. For any of these delta E, delta Y's, we'll just linearize it. So row measure order, lay it out, right? Just like what we did for the filters for inference. And then we take the input. Okay, so that the original inputs will be used to do the matrix multiplication by straightening, right? By straightening the convolution patch, right? Each patch of the convolution into a straightened path. So in this case, 1, 2, 1, 1, 1, 2, 1, 1, right? We've already gone through that in 408, and I talk about it again in the video, right? So this will be the matrix formulation. So we're going to do the next one. So the next one will be 2, 2, 0, 1, 3, 2, 0, 1, 3. And so we will be laying out the entire input matrix into the matrix multiplication form, right? And so this is going to be, generating one output, right? One weight, one essentially the gradient for one filter, right? But if we add another delta E delta Y for another feature map here, then we will be generating another filter based on the same input. If we attach more inputs here, right? Actually, attach more input in this direction. Okay, up. If we stack another input up here, then we will be generating. No, this way. Attach more inputs in this direction, then we'll be generating more filters, even more filters. So we'll be generating combinations of input and output feature maps for all these in this direction or in this direction, right? So we're generating more and more of the feature maps by expanding, adding more of the output feature map filter weights, the output feature map gradients, or attaching more of the input values. So this allows us to do the following. Remember, each input matrix is supposed to be used multiple times, one with each output feature map. So the matrix multiplication formulation allows us to naturally reuse the elements with this in a tiled matrix multiplication algorithm, right? So this should give you the same properties as the original 4 inference. But there's an important difference. What is the important difference between this one and the 4 inference? I keep talking about that dimension, right? The dimension actually matters because this thing is actually quite long, right? This is the output feature map dimension. So this thing is actually going to be, straightened by a pretty big square matrix, right? So this thing is going to be quite big, okay? And the fact that this thing is quite big means that you're going to have a larger replication factor.
Exactly.
Right? Because you're replicating, you're replicating for every element in your convolution filter, right? So the number of elements here defines the length of this thing, right? So it defines the amount of replication that we're going to need to make for the input elements. So if you go through the 408 notes, you'll realize that whenever we use bigger and bigger convolution filters, our matrix formulation is going to require higher and higher level of element replication for the input elements, right? The fact that we're using small filters, right, in the convolution layer, we typically use 3 by 3, even 1 by 1 in a lot of these the neural net models, means that we're not going to be replicating the elements that much. But as soon as k becomes big, when you get to 5 by 5, 9 by 9, the amount of replication becomes important, right? Becomes big. And now we're talking about potentially 100 by 100, 1,000 by 1,000. Okay? So we can be talking about thousands of times of the replication of the input elements. Okay? And that is a big problem because you will be getting to the point where you cannot even hold the converted matrix in your GPU memory. When you make, when you replicate these things by 1,000 times, 1,000,000 times, you can easily just, your input feature map into by this kind of factor, you can easily run out of GPU memory. So that's the reason why, if you use this kind of method for training, you should never realize this matrix. This matrix should not be explicitly stored in the memory. They should be dynamically assembled in the tiling algorithm. They should be fetched from the original. So this, when you load a tile like this, the entire tile should be actually assembled from the original matrix. Remember, we talked a little bit about that in the project. The best matrix multiplication algorithms, even in the forward path, will not explicitly, store the converted matrix. When you load the tile, you actually fetch the tile elements from the original, input, right? And here it's even more important because if you're not careful, you can actually be blowing up your storage by thousands of times, or even sometimes millions of times. Okay. Any questions? Yes.
The partial of E with respect to Y, that's always going to be all ones, right?
Which one?
The delta E over delta Y.
Oh, no. This is definitely, remember, at the very end, when you are doing just let's say a linear subtraction and absolute value, yes, that would be 1. However, remember, we're back propagating. So the delta Y, delta E will be eventually propagated into delta Y, delta X of the layer, right? And that layer, that input to this layer will become the output of the previous layer. So those values will become delta E, delta Y of the previous layer. I'm actually going to go into that.
So for the very last layer,
yeah,
first time it's performed, it's
most likely 1. But if you use Euclidean distance, then it will be a little bit funkier than 1, right?
okay.
Right. Or cosine distance. So it could be kind of funky.
Okay.
Yes.
So for this, can I do not actually generate this reshaped input feature map, but can I map the index to the real
Yeah, exactly.
address?
Yeah. Usually that's how things are done.
Okay.
So this gets back to the point. A lot of this model frameworks, right? TensorFlow, MXNet, and so on. They all say that we use GPUs, right? We use matrix cuPlus, and so on. But if you think about it, there's so many more details about than just that, right? How are you really using cuPlus? Are you explicitly generating the entire matrix and then call cuPlus? And for this kind of stuff, it could be a disaster, right? So the details of how the cuPlus is actually used and how the replication is realized, either in the shear memory level or in the global memory level, all these details can change your result performance dramatically, right? So that's why it's not about I'm using cuPlus and then I'm going to be fast. It's really about how you're using the cuPlus. And are you using some kind of internal function interface so that you can do the dynamic assembly and so on properly, right? And some of these frameworks are written in the language, in such a language that it may not even be possible to be able to to use some of those finer grain API functions and so on. Okay? Okay. So now we have figured out delta E, delta W for all the filter elements, right? With all that convolution calculation, you have all the delta E, delta W's. And every element of that big matrix tells you the importance of the filter value for the error, right? For the error that appears, the error as of the output of this layer, right? Because that's how you propagate it. So then, in general, we will be doing a change of the W value. So we know the importance, and now we're going to go and change the W value, just so that the next inference the W values will be right for this batch of input, right? So the way to do the adjustment is by subtracting a linear scale of the delta E, delta W. So every element of that filter is going to be adjusted by taking the importance of the element multiplied by a constant lambda. The lambda is usually a small value called learning rate. And then you subtract that value. You subtract the product. What's the rationale? This thing is telling you, if I increase the W a little bit, how much of the error is going to increase? If this value is positive, that tells me I should decrease the W value, right? And the more the error is going to to increase, the more I'm supposed to be subtracting from the W value, okay? And if the value is, you can also argue that you should be dividing, okay? You can argue that. But remember, when these values are small, dividing is actually the same as subtracting. Because when you do the Taylor series expansion, inverse is actually just subtraction, right? So that's why it doesn't matter whether it's division or subtracting, as long as the values are small. If the values are big, all bets are off, okay? So you cannot deviate from the original value very much. That's why you need to do a very small value here. So essentially, this is a small value that makes sure that whatever adjustment that you're making is small enough that the Taylor series approximation actually works, right? So you do a little bit adjustment, and make sure that in the end you can converge. This is, if you do enough of these adjustments, if you run a batch of inputs through, you say, oh, I need to do back propagation. You do the back propagation, and then you do this subtraction for all the values, and then you say, okay, let's run the values through again, okay? And until I no longer need to adjust the values, right? Because the values are good enough. I don't need to adjust anymore. All the errors are within some tolerable range, and then I'm done. So that's the convergence. Okay? Good? Good? Tired? Okay. But good, right? Okay. So basically this is the picture I want you to keep in mind. We calculated the delta E, delta W's, right? So they are exactly the same as dimensions as the original weight matrices. You just do a linear scaling for all the elements, and then you just do the element-wide addition, right? And then subtraction, and then you get the next line. Okay? Nothing fancy, just kind of so that you have that mental picture. Now, so the back propagation, for convolution layer is fine up to the delta E, delta W. But remember, this is not the only layer you're going to need. You're going to need to adjust all the layers. So let's say you're done with this convolution layer, but you have another convolution layer that you need to adjust, or all connected layer whatsoever. So basically, you need to also derive the delta E, delta Y for the previous layer, right? Remember, that's where we started for that layer. So that's why this is the obligation of each layer. You not only need to adjust your own weights, you also need to make sure that you generate delta E, delta W, delta X for yourself. Because delta E, delta X for yourself is the delta E, delta Y for the previous layer. The output of the previous layer is the input to yourself. So if you can generate delta E, delta X for yourself, then you prepared for the next layer, right? So that will complete the back propagation. So that's why the second step you need to do for each layer is to calculate delta E, delta X. What is delta E, delta X? By now it should be very clear. It's the importance of every input X element to the error. Right? So they should be of the same dimension as the input feature maps, right? Okay, so that it should be very clear now. So when we look at the importance, the way that we should see it is that the input feature maps are here. And how important are each input feature map? Each input feature map is going to be multiplied by the weights, right? So their importance should have to do with the weight values, right? The bigger the weight value that they're multiplied to, the more important these x values are. So whenever you adjust that x value a little bit, the effect on the error should be magnified by the weight values. So you should see some kind of weight, some kind of multiplication of the weight to the errors, so to generate the importance for you, right? So you should expect that. So that's exactly what the mathematicians will tell you. It's very natural. This is the